Okay, welcome back, everyone. I hope you are interested in the GraalVM, because then you're in the right room. Please welcome Thomas, who's going to talk about its journey from a research to a product.
Thank you. All right, yeah, hello, I'm Thomas. I'd like to take you a little bit on a journey of how we developed GraalVM and how we got where we are today. The talk will include some of the lessons learned, some of the things kind of that worked out very well, but also like the things that kind of didn't work out that great as we thought. And so the way it got started is actually quite some time ago. And one important thing that I think was true also for this project is like, when you start with such a thing, you gotta be bold and foolish. Because if you kind of realistically like assess what will follow, or kind of the amount of pain and work you will go through to make this successful and the luck you will have to make it successful, you probably, rationally wouldn't even start. And so for the Graal project, it started in 2011. So it's now like 13 years ago. And I was a student, fresh from university, full of confidence. We're gonna rock the world, okay? And we started in the research lab in Oracle Labs. And we were really very confident. So we started to do research vision papers. And the first vision paper on GraalVM, and it's kind of a fun one. Appropriate title, one VM to rule them all. And so we started off with this idea to create one virtual machine that would rule all programming languages. That was like the idea behind it. And it was primarily, if you look at the author list here, right? There was like kind of 2 people from Oracle, and then like a bunch of students from Linz University, another university, and so on, right? And so it was really, really very unexperienced team. And over time, actually, almost everybody on this list is still working on the project, on the team, and they all were on this journey with me over the last 10, 11, 12 years. And some of the core ideas in this paper were actually really still valid. I mean, some other stuff might have been a little too optimistic. But yeah, while we were very creative in naming research papers, the project itself, we named it back then C1X for hotspot, which, it was a descriptive thing of what we started off with, right? Because C1 is the code name for Hotspot's client compiler. It's the first tier compiler that compiles your method before it goes to the second tier compiler. And X meant this was the version of the client compiler that was ported to Java, because it's written in C++, but we literally copied the code and ported it to Java. And then we integrated it into Hotspot again. And this was like the first version of Graal, because the idea was like, oh, Java is such an awesome language, so let's just, have a Java JIT compiler that is integrated in Hotspot and running your Java programs. But thankfully, some of the more experienced members on the team were saying, this name, you're not gonna that's not gonna fly. That's not gonna make you, a good product. And that's where we later changed the name to something a little bit more reasonable. So for myself, I started out as a researcher and programmer in this project. And from then on, my career felt a little bit like a frog getting burnt. Because as the project grows, you get more and more into kind of this management stuff. And kind of your team size grows, and you need to do less and less and less of actual programming, right? While you feel it's necessary for the project to succeed, I kind of missed the times a lot when I was a programmer somewhere, and really do actual work. And the other thing you could ask yourself, when you look at this like CV here, like why are you like at the same company for 13 years? Oh my God, that's a long period of time, right? And so one of the things here is like when you build up such a team, it's actually quite difficult to change your job, because yes, I can change my job, but like I kind of can't like take the whole team with me, right? And as you build up your team and you build up your project, there's a certain level of attachment that's kind of keeps you at that place, right? And so this is something where as the project grows, you kind of forced into these things. And while initially we started out with 2-3 people and a bunch of students, like now it's like a very large team and a very large organization, and it's working very differently than before. Right? But I'm happy to say that a lot of the people who were there like 12 years ago, they're still on the team in different roles, and we kind of like the number of people that actually left us is like very low. But so the second thing, which I think is underrated sometimes, is that constraints that you have actually sometimes really force innovation. And if you wouldn't have those constraints, you wouldn't like be like actually inventing something. And for the Graal project, this was specifically true in one area, because one of the things in the Graal project was that, well, we created this Java JIT compiler, which kind of makes sense, and Oracle is has Java as a language, is the steward of Java, so it makes sense to invest in Java. But we as researchers, we really wanted to go polyglot. We wanted to not just be limited to one language, one platform. We wanted to go polyglot and compete also with other language runtimes, including JavaScript, Python, and so on and so forth. And that was also because I was like, before I joined Oracle, I did an internship at Google working on the V8 crankshaft compiler, right? And I'm a very competitive person, so I wanted to like compete with my old team, right? And be like, yeah, we can also do JavaScript here. And the fun thing was also that during my work on the JavaScript engines, it was clear to me that there's actually not that much kind of difference in the different VM components in a JavaScript VM and a Java VM. It's actually very similar, and there is a lot of duplication going on in terms of work, because if somebody improves the garbage collector of V8, right, it's not like helping the garbage collector in Hotspot, or if somebody creates a compiler optimization in V8, it's not helping Java developers and so on, right? And therefore, I thought it would be really nice if you can create this one thing for everything. And we tried to kind of do a JavaScript-specific front-end to our compiler, but it was really hard to do. We got like a little stuck. It was like a little bit too much work for us, because specifically the problem was like management didn't give us any budget for this. Because management, like, there is no money in JavaScript engines. Like, what do you do here? Do your Java thing, right? So management actually didn't allow us to kind of work on this with some budget. So we had to kind of find a way to have some small, like, small part of the team or budget like carved out for this, with management not really caring or noticing about it. And so we found an unsuspecting master student. Because we had these research collaborations and we had a little bit of money left over. So we got like a half-time master student for half a year to build a JavaScript engine. And on top of Graal, right? So and then we're like, okay, this approach with this front-end thingy, it kind of doesn't work because it's too complex for that master student to implement, right? And that is when we're really thinking hard and came up with maybe the most innovative idea that we have in GraalVM, which is this, what we call the truffle framework. And it now gets a little bit technical. I like to share this idea because this is one of the things that really is something in the Graal project. As a user of Graal, you might not notice these things, but it's one of the most innovative parts of it on the polyglot side. So what we did is like, okay, the compiler frontend is hard to do, but everybody can write a JavaScript interpreter. That's not that hard, at least for a subset of the language. We didn't have to support everything in the initial version, just enough to get a prototype going, right? But like you can write a JavaScript interpreter, right? And now the idea was people write this JavaScript interpreter, and what we do is we use partial evaluation of the interpreter to derive the compiled code automatically. So the compiler doesn't know about JavaScript itself. The compiler only like sees the interpreter entries and the interpreter code. And when a certain method of JavaScript gets hot, so a method is executed very often, then we are effectively moving, inlining through it. We create a special compilation where we inline through the interpreter. We start from the interpreter entry, and we do a massive like targeted inlining of everything that we see and copy the code out into a partial evaluated compiled function. When we see here two examples, we compiled function X, we compiled function Y, and the important part here is that the whole definition of what is JavaScript semantics comes purely from the interpreter definitions. So there is no JavaScript specific thing in Graal, and at the same time, the student could work on that interpreter without knowing anything about Graal compiler optimizations and so on. So it's a real like nice separation of concerns, and this is what enables us with Graal to, in relatively easy fashion, implement a bunch of languages at the same time. Like we have a Ruby implementation, we have a Python implementation, we have JavaScript, we have WebAssembly, etc. And all of these work on the same principle. Actually, the Apple Pickle language that came out just like last week, it is built on this system. It is using exactly that technique. It's built on Truffle, Graal, and this partial evaluation system. But in this case, again, like if somebody nowadays would give me the task, right, and say like, here's 5 engineers do a JavaScript engine on top of Graal, right? I wouldn't even think to come up with this type of approach, because it wouldn't be necessary, right? So it's a case where the constraint of really not having the budget and really needing to find a solution that's simple enough, right, that was forcing us into this type of innovation. And we published a paper later on this, which is called Practical Partial Evaluation, where we are demonstrating how this works for multiple languages, etc. Now, the other thing, we did a lot in the project, and I think it's necessary for such a project, and it's like was the approach of like throw a lot of stuff at the wall and kind of see what sticks, right? And what I mean by that is that as you build your project, your project can do many different things, and sometimes we depicted Graal as a Swiss Army knife. That's like this complex thing. It can do this, can do that, etc. Right? But as you build it, as you yourself build it, you don't know yet how people are gonna use this Swiss Army knife, on which tools on that Swiss Army knife people will find more useful than less useful, right? And so what we did with Graal in this case is when we published it first time open source in 2018, so already we were like developing it for a very long time as a research project. But in 2018, we finally decided, okay, we can run a lot of interesting things. Let's go out there and publish it, so other people can play with it. And what we did there is we had a blog post called Top 10 Things to Do with GraalVM. And in this blog post, we just put every potential imaginable thing you could do with this technology. And the blog post, we were very lucky. It was like back in the times, Twitter got us viral, and like there was a lot of people looking at it, and then people actually started playing with it and gave us feedback on which of those parts were interesting and which one less. And I like to go a little bit through this list and go a little bit kind of in hindsight which of these things we thought would be really cool and didn't work out, and which of these things actually worked out. So from these 10 points that were published back then in this Medium article, well, we really thought that compiling many languages together would be really like exciting. Unfortunately, like this kind of didn't really take off very much. So the idea of combining Ruby and JavaScript at the same time and so on, right? It's something that we found potentially interesting, but it turned out to be just not practical, or people didn't really want to run this in production and so on. So it's one of the parts that kind of we thought were interesting, but didn't quite work out. Also on the tooling side, we do have tools that work across many languages. And we developed quite a bit of them, like we have a profiler, we have like a debugger, all of this across languages. But it didn't work out so well because I think people that write in a specific language, they're not willing to do compromises easily. And a tool that sort of cross-language still has to sort of be on the common denominator. It needs to, like, it might not be the best tool for this language, not the best tool for this language, and so therefore people don't necessarily like it that much. Now, the other thing is running native languages in the JVM is something you can do with GraalVM, which is fun. You can take a C program, compile it to LLVM bitcode, and interpret it on the JVM and like JIT compile it. We had a few uses of that in the sense that some people that are really, really concerned about security, they liked the bounce checking of this. But overall, it's something that, again, you know, it wasn't taking off very much. Also, this thing of extending a native application, you can with Graal, you can take your Java code, like compile it into a native library, and then link it with a C library. I think it's an interesting thing, but apparently nobody really was interested in that. And now we get to the parts where it gets a little bit, where there was some usage and where people were starting to get a little bit more interested in it. One thing was Java code as a native library. So we use it ourselves as well. When you are running the Graal JIT compiler in your hotspot VM, you're running it pre-compiled with Graal into a native library. So the JIT compiler is written in Java, but we are running it as a native library, then integrated somewhere else. And the other thing was create your own language. We had this truffle framework, right? This awesome framework to create languages. And we have a few users. I mean, most prominently recently now Apple, that's built on top of that. Now we have a few startups that built their own language on top of it. It wasn't like taking off as much as we'd like to, but we see more and more evidence of people with small languages that like the fact that if you implement the language on top of our system, the effort is much lower, and you get a lot of like utilities for free for your language. So for domain-specific languages, it is something that worked out reasonably well. And now to the things that I think worked out quite well in the project. The first one is high performance modern Java. So in Graal, when we built the Graal compiler, it was itself written in Java. So everybody on the team is writing Java on a daily basis, which helped us actually in terms of like finding more compiler optimizations that are targeting Java code. Because if everything you think about every day is Java code, you're going to write, you're going to be more likely to find such opportunities, right? Whereas other Java JIT compilers that are written in C++ have not this advantage, right? And the Graal compiler in general can execute your Java program about 10 to 20% faster on average. Like there's different workloads, of course. And we kind of have a really like nice modern JIT compiler that's actually written in Java. Now, the other thing that actually worked out almost better than we expected was extending a JVM-based applications with a dynamic layer on top. And this means that you would have, for example, a platform that's written in Java, but then you have like a JavaScript execution like on top of it as an extension. This is something that's in production at Oracle at the big NetSuite project. We were also recently approached from Amazon that they themselves use the same approach in a very large part of their internal products. So this type of like using Graal as an extension mechanism to an existing Java platform, that one is quite popular. Now what worked out also was polyglot in the database. And this, of course, has to do a little bit with the company working it, because if you work at a big company and you want to get funding for your project, right? You want to attach yourself to the flagship product, okay? So at Google, you want to do something for search, right? And at Oracle, you want to do something for the Oracle database. And this is why the initial funding for the project in the early days came from us saying, okay, we have this polyglot execution. We will integrate it into the database. And that's where we got our funding from. But it also worked out pretty well because as stored procedure kind of extension mechanism, it is an attractive option. And so therefore, there is this thing called Oracle Multilingual Engine that is using Graal and its compiler, JIT compiler, etc., to execute JavaScript in the database. And we have recently also started with the MySQL integration. So there's a prototype, I think, already. It will be GA pretty soon, where also in MySQL you will be able to start to use languages like JavaScript. And we are extending these languages. Because it's always an interesting debate of like, what code you should run in a database and what not, right? But like, having the option can be quite attractive because you can make your middleware thinner or completely gone if you can run more code directly in that database process. Now the thing that really took off, however, and this is what GraalVM nowadays is most known for, is low footprint, fast startup Java with native image. And that's interesting because, again, I mean, this is a story that's like the same for many successful products. Like this feature, we didn't plan for this feature at all. It was like a byproduct for us. It was like something like that kind of fell out of some other things we had to do. And specifically, this one here was a byproduct of our need to integrate into the database. Because as I said, our whole system is written in Java, and but now they asked us, oh yeah, put it into the database. So in order to do that, we needed to create a mechanism that is taking our Java code and compiling it and linking it with the database process. We couldn't like run another big JVM in there. It needed to be lightweight, small, and linking with the C code, right? And for this, we developed this native image capability. Now, when we published this, we still like talked about it, and then suddenly, like it felt like like the largest part of the Java server-side, server application community was like really excited about that feature. It was like Micronaut framework adopting it in the first month, and then Jfokus came out, Red Hat came out with something without even telling us that was pretty much built on this thing, which is Jfokus. And then also Spring people were like, oh yeah, we need this as well, right? So suddenly a lot of people were like interested in this. And while in the beginning of the project, we tried to fight this a little bit in the sense that we said, yeah, this is cool, but look at the other 9 cool features over there, okay? and GraalVM is more than that, right? And so for us, it was sometimes a little bit too much. We were like, okay, but in the end, we're like, okay, fine. I guess this is where a lot of people see a lot of value, and that's why nowadays we kind of almost go with like, okay, GraalVM and native image is the thing, right? But the other aspect of this was, of course, because we never designed this feature for this broad adoption, there were issues with it when people started to use it in this broader context. Because we ourselves were using it for our own like program, and therefore it had a lot of limitations that we were like, because we needed to be fast to implement this thing. So we cut a lot of corners. They were like, yeah, we don't need this feature, we don't need synchronization, we don't need reflection in our code. Everything that we didn't need in our code, we didn't support, right? But now suddenly with everybody, using it, more and more people were like, oh, what about you also add this feature, and I need to have, my reflection config work, etc., right? But this is now, and then we went through some period of pain because like we suddenly had more users than we kind of expected, and they had different, like, expectations. But I think this settled then over the next years. But we were pretty busy over the next years then kind of adapting this feature to something that is actually broadly usable, right? And but I'm like over the years nowadays, I think we kind of could mitigate this like pain points, and I will have later more details on why I think this is really an exciting thing for Java. Now, the other thing is an interesting takeaway for us, or what we learned, is that most programming languages lack specification, which is sad. Because we wanted to polyglot, right? And we did this JavaScript prototype and the Python prototype and the Ruby prototype. And the first prototype for all these languages was really easy. It was like not a problem. And you can run your hello world and you can run your small program and not a problem, right? But then we figured, oh, how do we get now a fully compatible Python implementation, right? And we coming from the Java world, right? We are like a little spoiled. In Java, every Java version has a Java language and virtual machine specification document that says exactly how you should behave under what circumstances, and which allows multiple implementations to coexist. And it's not just that the language is specified. What is very well specified in Java as well is the native interface. So this is the Java native interface specification, version 1.1 from 1997 from Sheng Liang. And this one is, if you read through that, you will recognize nowadays GNI. And this native specification is actually quite important, such that you can actually kind of carve out what is like your managed runtime versus what is the native code. Because the problem is, well, let's talk about Python. And in Python, in the Python documentation, it says, yeah, extending Python with C or C++, right? Which is a common use case for Python developers to do, because Python itself is interpreted, so it's not as fast. So whenever you want something performant, you write it in C, C++ and connect it with Python, right? But now in the documentation, it says, well, the Python API is incorporated in a C source file by including the header python.h. Okay, you need to include a header file to write your native extensions for Python. Makes sense to a certain extent. But then you kind of look at that header file, and yeah, the top part of that header file is taken from GitHub here, includes a lot of stuff, right? And if you now run the C preprocessor on this and figure out how many methods are defined here, right? Then it's 1,281 entries. So the Python native interface is 1,280 methods that you could potentially call, and the way you write a Python extension is like you have this include file, but you're allowed to call any of those, and there is no other specification around. So now, of course, thankfully, most extensions might behave nicely and not call something obscure, but in theory, any extension can call any of these 1,280 methods for its purpose, right? And this is actually a problem even for Python itself, because it means that in the Python interpreter, if you change one of these methods, you're creating an incompatibility with your ecosystem, right? And for us as language implementers now, is the problem if I now have an alternative runtime. I have now the GraalPy, which is our Python implementation runtime. I need to implement these 1,280 methods. Otherwise, one of the native extensions might not work, right? And the problem with this like one extension might not work thing is that, well, it might not sound so bad, if 1% of the packages don't work, but it sort of accumulates, because the average project has a dependency tree with hundreds, if not thousands of dependencies. So if 1% doesn't work, like you can imagine, like basically, you cannot run 90% of the apps anymore. because it accumulates across your dependencies. So in order to be compatible in a reasonable way, you need 99.9% of packages to work. Right? So in Python, we actually have an initiative there that we do with the Python community, which is called HPy. This is a new standardized interface for Python, where we are developing something that's a little bit similar to JNI that should help the ecosystem. And we are currently working with the Python ecosystem to make sure that core packages are ported from Python H to HPy, which is smaller interface and that is less dependent on the actual runtime. And it should help the Python community as a whole, and it's very well received in that Python community. It's the HPy project, right? And we have this problem not just for Python. We had this problem also for R, which is a statistical language as well. We have this problem for Ruby. Thankfully, we didn't have this problem for JavaScript, because JavaScript itself doesn't really have a native extension. Now, Node.js does have a native extension, but it's reasonably defined. It was like v8.h, which is the header file of the v8 engine. But in general, when we implement those languages, implementing the core of the language, even for complex languages, is like pretty easy. It's not the biggest effort, but making the C extensions run is what really, really is then taking all this time. And we kind of underestimated some of this, to be honest. We were a little bit too optimistic to our management on some of this. We're like, oh yeah, we're gonna be like, we'll have this Python runtime, next year, and then next year comes and still cannot run big stuff because of this problem. If one dependency fails, you're like screwed, right? But we are getting there, and we continue to invest quite heavily, specifically in Python. We currently have Java and JavaScript as languages that we would call production, because we are like super compatible on the JavaScript standard and so on, right? And Python will be the next step for us. And you can run larger things already in our Python implementation, but we still have some work to do before we call it full production, and we are putting quite some efforts into that. Because we think that Java, JavaScript, and Python would be the three major languages that we should support. Because those can cover a lot of use cases. And for Python, because we have the Java interoperability, what this will allow you is that you can use a Python library, TensorFlow or Matplotlib, or for painting something or similar from your Java code. So you don't need to like switch. And I think this will be a very interesting extension of the ecosystem for Java developers. All right, so one lesson we learned over the time is that ahead of time compilation is better than just in time compilation. So now I'm like in my university research, etc. Like I'm coming from a just in time compiler world. So we were like doing for almost 20 years, 15 years, research in just in time compilation. But like if you research something really for a very long time, you get to know all the disadvantages, and you finally know what's like some of the problems with it, right? And as you could see with the Graal project, like the head of time compilation capabilities, people found more exciting than our just-in-time compilation capabilities. And that's why in GraalVM, what you can do is you can not just take a Java class and run it as a JIT mode. You can do that as well, but you can create a native image out of it, which is a self-contained binary, and run it. Now, why would you care about this? Or what are the operational metrics that you would optimize for if you do this? And the first one is memory usage. So what happens in JIT compilation is that there's a lot of memory wasted by the JIT compiler itself, by the profiler that looks at the application, and by the application metadata that needs to be kept around. Second, you want to have a good throughput, of course, right? You want to have good tail latency, and you want to have good warm-up and startup, right? And what we did with GraalVM native image recently, and this is now becoming a little bit of a sales pitch. Yeah, excuse me for 2 minutes. We are running a Spring Pet Clinic application, and we're running it in ahead of time compile mode and compare it with hotspot JIT mode. And what's happening is that, of course, when you run a Java app, you can configure it with different memory properties. And people actually typically just, they take a Java app and put in a large number for XMX and be like, okay, that's probably okay, right? And that means in the cloud, actually, I think 90% of apps are completely over-provisioned with memory. Now here we did an interesting experience. We took this application and we configured it with different XMX numbers. And we measured the throughput you get, right? And as you could expect, like if you give it very, very little heap, like the throughput suffers, of course, because you're like kind of occupied with garbage collection. And then you give it more and more heap, but then at some point for a certain app, kind of the return of investment of giving it more heap is like coming smaller and then completely flattening out, right? So for this app, then after about 2 GB of memory you give it, like you don't get more throughput anymore, right? What you can see in this graph already as well is that, well, native image consistently, despite being configured with the same garbage collector, this is using the same garbage collector with the same heap setting, uses less memory. And that's because that's the delta. The delta you see here is kind of the memory that's consumed by JIT compilation and its metadata. Now, the other thing is, yes, exactly. So this is kind of the memory you configure and the memory the VM takes. On the right is the memory you configure and the throughput the app takes. Yeah. So the throughput it takes is kind of it's sort of a curve that at some point doesn't like increase anymore. And what we can now do is we can now overlay those two graphs and create a metric that we call operations per gigabyte second. The other place where you find this type of metric is on the Amazon Lambda pricing page. I see some laughters in the audience. I guess more people looked at this. So in the end, in most cloud environments, you are paying for gigabyte seconds. Like how long do I occupy a certain instance with a certain amount of memory. And here I can now, by overlaying those two graphs, I can get the operational efficiency of a certain max heap setting. And we can see there's a clear peak here, where around 500, 600 megabyte of max heap setting is my optimum. I might not have the best throughput at this point, but my throughput per memory occupied is the best, right? And for an application that's scaling, or if I'm an application where I'm considering how much cost it is to run it, this is where you want to go. What we can also see is that operations per gigabyte second for native image is double as good, like in native time compilation is double as good as the JIT version. So to summarize this now, on the operational metrics, like native image on this application configured with 512 megabyte of heap takes 40% or almost half of the memory. The throughput is slightly higher, so you have no throughput cost whatsoever. The throughput per memory, therefore, like the multiplication of these metrics is 50% better. The tail latency is better because garbage collection becomes a little bit simpler in ahead of time compilation, and JIT compilation can interfere with your tail latency. And startup is 34x faster, of course, right? I mean, startup is much better, like everybody knows that, right? I mean, that's a no-brainer that if you ahead of time compile, your startup is going to be better, right? But apart from the startup, and initially we just had the startup, right? But that's another thing, when you develop this new technology, your initial version might be really, really good in one aspect, and that's already good to kind of excite some early adopters, which is great and important. But then, to get like the vast majority of people, you need to get rid of all regressions. People don't hit more than regressions. There must not be a regression anywhere. And that's why over the time, and in the initial versions of native image, for example, the peak throughput was actually lower because we didn't have all the optimizations going and so on, right? And so that's why in the initial versions, people were like, oh, I cannot use this because peak throughput is low, right? But over time, over the next years, we had to kind of, to get more mainstream, we had to get rid of all the possible regression such that you have the advantage, but you have no like regressions on other metrics, right? And there's a few other things actually that are benefiting here. We are better on all operational metrics, but so there's also the thing that like with ahead of time compilation, you get a predictable performance. So the performance is not changing between runs a lot. And you get an improved security profile because every code that is there is actually, like only the code that is reachable is actually compiled in there. And a lot of security problems comes from, you know, random code being executed or reflectively called that you didn't expect to be called. Like in Java, there's a class called UL class loader. I mean, every security person who looks at this class will be like, what is this, right? It loads code from a random endpoint and executes it, right? So this kind of thing is like, not possible in our native image setup, but it adds to the overall security profile. And yeah, some other fun thing. Who has heard about the 1 billion row challenge? Perfect. Yes, I see. Yes, perfect. Yeah, so the 1 billion row challenge was just going, and I don't know if you followed it, but if you followed it, you saw that I was very excited about it. The reason is, well, there's two reasons. One reason is in my time when I was 15, 16, I was competing really heavily in international Olympiad in informatics and ACM contest and these type of things. So it brought me a little bit back to my youth times. And the other thing, it was the perfect excuse for me as management to do some coding. So that was also a thing. And if you look at my GitHub, where's the green bars where I do GitHub activity, you will see the 1 month of the 1 billion row challenge going. And so anyway, but so the fun part about this was a challenge where, it was a fun challenge made by Gunnar Morling, who created this challenge to like, parse 1 billion rows in Java, which is a 13 gigabyte file, so it's not a small workload. It's really like doing something right. And then when you look at the final result table on the right, what you see is that if you look at the JDK that's used by 8 out of 10 of the top 10 entries, it's Graal, 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 right? A lot of those use Graal native image binary, which also shows that the peak performance of Graal native image is actually competitive. And this runs in 1.5 or 2 seconds here. So but the workload itself is not that small because this runs on 8 cores, etc. Right? So it's not the workload where Graal would shine specifically well, but still you could see how suddenly a lot of people who wanted performance were going for Graal native image. And the nice thing is not only the top entries were using Graal, but if you go to the entries that are less optimized and that are like just using Stream API and so on, them using the Graal JIT compiler is actually giving them also advantage. So if you don't want to go for this full optimization of hand optimization of your program, you can still just use Graal to be like fast in execution. And yeah, this challenge was really cool because it highlighted some Java performance aspects, and I'm happy to talk to anybody about my solution who want to come to the booth. It's very, very exciting stuff. All right, cool. Now, the last lesson here, and before I conclude the talk, is at least for a system like Graal, the ecosystem and early adopters are key to success to the product. And I really like to thank here also, maybe there's some people in here that use Graal, much earlier than it was ready, and felt some pain, etc. I really like to thank these people because the people that are willing to try out a new technology before it's ready, they are crucial because they are the ones that can give the feedback on things that you as a developer of the technology have never thought of. And for Graal specifically, this was super important, and we were very happy to see like quite some excitement in the ecosystem from some people who are just willing to try new stuff. And we also like to thank the people who did all these kind of frameworks. We have a Graal meetup, and we bring all the framework developers together. They're often very competitive, but at the Graal meetup, I have them on the same photo. Okay, was no fighting before, no fighting after. But so you could. It was very important for us, these web frameworks, because they were the missing piece on top of Graal that were very important to have. And they were the ones that were then like helping us get a larger adoption of the technology. And the ecosystem adoption wasn't just in the web frameworks, it was also at kind of the, nowadays every cloud API, Google Cloud, AWS Cloud, Microsoft Cloud, and Oracle Cloud all support native image. And it's really something that kind of also the cloud providers feel is important for their stack. Now, one thing, of course, is, a lot of success also gets you some haters, of course. Like there's always something also in the ecosystem as you kind of take some space, and the more space you take, right? Somebody might, feel like you are like going on the turf, etc. So this was, but overall for us, kind of the positive aspect of having early adopters that are excited about technology is certainly overwhelming, and we don't have time anyway and no space on the slide, so let's go next. Graal is an open source project on GitHub. It's a very active one. It's one of the most active. It's probably the largest Java open source project on GitHub. My team is maintaining more than 4 million lines of open source code on GitHub. You can check out on GraalVM.org and on GitHub what we're doing there. It's a large team behind all this, right? I mean, it's really like many people on the GraalVM team. Even if from a developer advocate, if I'm talking about GraalVM, it looks like I'm the face of it. But there's really a very large team behind it of super talented people, and they're like excited if somebody plays with the technology and looks at it. So with that, I hope I could give you a short insight into how GraalVM was developed and how we got there. I'd like to thank you for your attention, and I'm ready to maybe answer 1 or 2 questions. And otherwise, I will also be at the Oracle booth later and answer your questions in private as well. Thank you.
Yes, we have one question here.
Yes, a few years ago, I sat here and asked Mark Reinhold about what were the long-term goals for GraalVM in the OpenJDK. And he answered and said that one of the goals was that, or the problems that he had, it took over almost 2 years to make a new developer on the C2 to get productive. So he said that one of the goals is to get rid of C2 and get rid of C++ within the JDK. And I'm still waiting.
Yes. So the question of when are we going to replace C2 and so on, right? It is true that, of course, Graal is, the Java community should be really proud about Graal because it is written in Java. It shows a JIT compiler can be written in Java. It doesn't have to be C++. And it's one of the only instances. It's not like the JavaScript people are writing the JIT compiler in JavaScript or anything, right? So it really shows the performance aspects and broad aspects of using Java for this compiler. It has also practical advantages because Java has bounce checks. So a certain category of compiler crashes just can't happen, right? So all of this is really cool. We have started Project Galahad to continue maybe with an OpenJDK integration. Now, of course, Graal is a very large open source project. OpenJDK is a very large open source project, and so integrating and collaborating between those two can take maybe more time than some would expect. So we don't know yet exactly when the OpenJDK community will pick up more of Graal technology. Like from a GraalVM team's perspective, we're certainly ready to contribute to OpenJDK. But you also have to say that Graal itself it's more than a Java JIT compiler. It's one aspect of it, and the Graal project itself will also continue some of the polyglot aspects, Python aspects, etc.
Thank you. I think we will take the rest of the questions offline.
Sure, yeah, let's take it offline.
Minutes.
Thank you so much for coming, and let's talk at the booth.